In Digital 2 of the You Can Do series, you saw how numbers were added together in circuits referred to as adders. You learned about the half adder and the full adder devices. Now you will learn how numbers are subtracted from one another. We will begin our study of subtraction by examining the complement of a binary number. The complement of a binary bit is nothing more than its inverse status. In other words, the complement of 1100 would be 0011, or the complement of 1010 would be 0101. As you can see, to make the complement of any binary number, you simply change all the ones to zeros and all of the zeros to ones. The first method of creating a complement number is often referred to as ones complement. As you shall soon see, we can subtract any number by adding its ones complement in a certain way. As you recall, the rules for binary addition were simple. They were 0 plus 0 equals 0, 1 plus 0 equals 1, 0 plus 1 equals 1, and 1 plus 1 equals 0, carry 1. And the rules for binary subtraction were equally as simple. 0 minus 0 equals 0, 1 minus 0 equals 1, 1 minus 1 equals 0, and 0 minus 1 equals 1, borrow 1. The alternate method of binary subtraction involves the use of ones complement. To better understand how the ones complement works in subtraction, we will demonstrate with a couple of examples. In the first example, we will start by subtracting decimal number 3 from decimal number 5. 5 will become the minuend, and 3 will become the subtrahend. First, we must convert the minuend and subtrahend into their binary equivalents. Next, we change the subtrahend into its complement number. This changes the binary 3 into 100. Then we simply add the numbers together. We know that 1 plus 0 equals 1. 0 plus 0 equals 0. And 1 plus 1 equals 0, carry 1. Next, the one bit that was carried is added to the least significant bit to the total sum. When we do this, we see that the answer is 010 in binary, or 2 in decimal. This time we will subtract decimal 6 from decimal 14. As you can see, the binary equivalent of decimal 14 is 1110, and the decimal equivalent of 6 is 0110. First, we find the complement of the subtrahend. Then we simply add the complemented subtrahend to the minuend. You already know that 0 plus 1 equals 1. 1 plus 0 equals 1. 1 plus 0 equals 1, and 1 plus 1 equals 0, carry 1. Next, we add the carry bit to the least significant bit. 1 plus 1 equals 0, carry 1. 1 plus 1 equals 0, carry 1. 1 plus 1 equals 0, again carry 1. And 1 plus 0 equals 1. When binary number 1000 is converted into decimal, it equals 8, which is the answer to our problem of 14 minus 6. Another common complement method is called 2's complement. In the 2's complement method, the subtrahend is complemented by changing the zeros to ones and the ones to zeros, just as we did in ones complement, but this time the extra 1 is added to the subtrahend before it is added to the minuend. The last carry product is then omitted. In this example, we will subtract 9 from 12. First, you must find the complement of the subtrahend. Next, you simply add 1 to the complement's value. Then you add the 2's complement value to the minuend. 0 plus 1 equals 1. 0 plus 1 equals 1. 1 plus 1 equals 0, carry 1. And since we carried 1, we now have 1 plus 1 equals 0, carry 1. Since we had already added 1 to the subtrahend, we discard the carry bit, and our answer becomes 0011, or 3 in decimal. Next, we will examine the multiplication process used in microprocessor-based systems. Microprocessors are designed to perform addition problems at an extremely fast rate. The microprocessor can also be programmed to multiply by performing a series of successive addition steps. We will now examine one such circuit. Here we see a simple 4-bit binary multiplier using the successive addition process. Notice that the multiplicand is placed on the A inputs of the 4-bit parallel adder stage. Also notice that the multiplier is nothing more than a down counter which controls the add enable input. The sum of inputs A and B are placed into an accumulator. The total in the accumulator is then fed back into the B inputs of the 4-bit parallel adder stage. And notice that the symbol used to represent the sum output is the Greek letter sigma. Now let's examine this circuit and see how it works. We will start by multiplying 3 times 4. As you may have noticed, the multiplicand has been loaded with the number 4 in binary, and the multiplier, which is in the down counter stage, has been loaded with binary 3. The accumulator has been cleared and is set to 0, 0, 0, 0. Since the multiplier has a binary number greater than 0, 0, 0, 0, it will enable the 4-bit parallel adder stage and cause it to add the binary numbers placed at inputs A1 to A4 with the binary numbers placed at inputs B1 to B4. You may have also noticed that a multiplier decreased by 1. Since the inputs A1 to A4 have a binary 4 and the inputs B1 to B4 have a binary 0, the accumulator will store the sum of binary 4. Next, the multiplier again decreases by 1, which in turn enables the adder stage to add the inputs of A1 to A4 with the inputs of B1 to B4. At this point, inputs A1 to A4 have a binary value of binary 4, and inputs B1 to B4 also have a value of binary 4. Therefore, the accumulator will store this sum as a binary 8. At this point, the multiplier will once again decrease by 1 and enable the adder stage, causing it to add the inputs A1 to A4 to that of B1 to B4. When the adder stage adds the 4 from the multiplicand with the 8 from the accumulator, the new sum will be 1100 or binary 12. When the down counter reaches 0000, it will no longer enable the adder stage, and the problem is completed. As you can see, multiplication can easily be achieved by using the successive addition process. Division can also be achieved by using a similar process, but instead of adding the values at inputs A1 to A4 with those of inputs B1 to B4, they are subtracted from one another in a successive process. Every microprocessor contains an ALU, or arithmetic logic unit, where the arithmetic and logic operations take place. The variety of operations handled by the ALU will depend on the type of arithmetic logic unit used. Here we see the SN74181 integrated circuit. It is a high-speed arithmetic logic unit that has a complexity of 75 equivalent gates in a 24-pin monolithic IC package. This IC performs 16 binary arithmetic operations on 2 4-bit words. One 4-bit word is placed at inputs not A0 to not A3, and the second 4-bit word is placed at inputs not B0 to not B3. The operations performed by this IC are selected by the 4 function select lines S0, S1, S2, and S3. When performing arithmetic manipulations, the internal carrier must be enabled by applying a load to the mode control input labeled M. A full carry look-ahead scheme is made available for fast simultaneous carry generation with a group carry propagate labeled not P and a carry generate labeled not G for the 4 bits in the package. The pin labeled CN is the carry-in input, and the pin labeled CN plus 4 is the carry-out output. The pin labeled A equals B is a comparator output, and the pins not F0, not F1, not F2, and not F3 are function outputs. The ALU works in conjunction with a number of registers which are used to temporarily store data and with a control circuit used to control the ALU. You will learn more about the arithmetic logic unit when you study microprocessors. The complement of a binary number is its reverse bit status. For example, the complement of 1110 would be 0001. There are two types of complement numbers, 1's complement and 2's complement. To find the 1's complement of a number, you simply find the complement of the subtrahend, then add the complemented subtrahend to the minuend. Then you add the carry 1 to the least significant bit of the sum. This method is used by digital circuits for subtracting binary numbers. 2's complement is very similar to the 1's complement in that you must find the complement of the subtrahend, then you add 1 to the complemented subtrahend before it is added to the minuend. The last carry digit is then omitted. Every microprocessor contains an ALU section where the arithmetic and logic operations take place. ALU stands for Arithmetic Logic Unit. This concludes our first review. Next, we will examine multiplexer and demultiplexer circuits to see how they work.